In the last example, we calculated several slopes of secant lines. We noticed that as the second point moved closer, the slopes were changing. Now, we're going to write a formula that represents that slope in general. The expression we've been using to compute the slope of a secant line appears so often in calculus that it has a special name: difference quotient. The difference quotient of a function f of x at x equals a is f of x minus f of a over x minus a. This should look familiar. This is exactly the formula of the slope of a secant line. This represents the average rate of change of a function over the interval from a to x. Now, we're going to rewrite this expression in a slightly different way. This new form will be very important when we define the derivative. If we let x be a plus h, where h represents a small change in the input, then we can substitute that into our formula. Start with the original formula, f of x minus f of a over x minus a. We will replace x with a plus h. In the denominator, we have a plus h minus a. A minus a is 0, so we're left with just h. This is the alternated form of the difference quotient. This form is especially useful when defining derivatives. Why? Because instead of thinking about moving from a to some random x, we're thinking about moving just a small amount h away from a. And later, we'll let that small change shrink towards 0. So here's what's happening. The difference quotient gives us the slope of a secant line. It represents the average rate of change. When we rewrite it using h, we are preparing to take a limit. That's how we'll get the derivative. So, the difference quotient is the bridge between the secant lines and derivatives. In the next step, we'll use this expression to actually compute derivatives. Now that we've defined the difference quotient, let's practice finding it for a specific function. This is where algebra becomes very important. We're given the function f of x equals x squared plus 4x plus 5, and we want to find the difference quotient. Here's the formula for the difference quotient: f of a plus h minus f of a over h. First, we need to compute f of a plus h. We use this function and we will replace x with a plus h. Now, we are going to expand this. A plus h squared is a plus h times a plus h. 4 times a is 4a, 4 times h is 4h, plus 5. I still need to multiply these two factors. A times a is a squared, a times h is ah, h times a is ah, h times h is h squared. Combining like terms, ah plus ah is 2ah. Now, we'll find f of a. We use this function f of x, and we replace x with a. So f of a is a squared plus 4a plus 5. Now we plug these into the formula. We will replace f of a plus h with this expression. A squared plus 2ah plus h squared plus 4a plus 4h plus 5. We will replace f of a with a squared plus 4a plus 5 and divided by h. Now we need to distribute the negative sign to every term in this expression. Combining like terms, a squared minus a squared is 0. 4a minus 4a is 0. 5 minus 5 is 0. And we have 2ah plus h squared plus 4h over h. From the numerator, I'll factor out h. So I have h times 2a plus h plus 4 all over h. H divided by h is 1. And I have 2a plus h plus 4. This is the difference quotient. Now, we are going to use the difference quotient to find the rate of change over the interval from 0.2 to 9.6. That means you start with 0.2 and you end at 9.6. So your A is 0.2 and your second point is at 9.6. H is the difference between the two x values. So H is 9.6 minus 0.2. Now, we substitute A and H in our formula. We will replace A with 0.2 and H with 9.4. So, the average rate of change over the interval from 0.2 to 9.6 is 13.8.